The moon, long thought to be a silent, inactive rock, is now revealing secrets that could change everything we know about our closest celestial neighbor. Renowned physicist Michio Kaku has issued a warning after NASA detected a mysterious seismic signal deep within the moon's core. This discovery challenges decades of assumptions and hints at dynamic processes that might even impact Earth over geological timescales. Today, we explore what this seismic activity means for lunar science, future missions, and our understanding of planetary evolution. The moon's hidden activity revealed. For decades, scientists believed the moon was geologically dead, its core solidifying and cooling quietly like a dying ember in space. But recent data from NASA's lunar sensors have detected unexpected seismic pulses emanating from deep within the moon's interior, challenging everything we thought we knew about our celestial companion. These signals suggest the moon's core is not just passively cooling, but undergoing significant changes that could reshape our understanding of lunar evolution. Physicist Michio Kaku has highlighted these findings in recent lectures, warning that the moon's internal activity could have long-term effects on its structure and even Earth's environment over geological timescales. This seismic activity challenges the traditional view of the moon as a static, inert body that finished its geological story billions of years ago. The discovery represents a paradigm shift in lunar science, forcing researchers to reconsider fundamental assumptions about how small planetary bodies evolve and die in our solar system. Inside the moon's dynamic core structure. The moon's internal structure resembles a miniature version of Earth's, with a solid inner core surrounded by a partially molten outer core that scientists are now discovering remains more active than previously thought. New analyses estimate the inner core's radius at approximately 240 kilometers, primarily composed of iron and nickel, enveloped by a fluid outer core extending roughly 350 kilometers from the moon's center. Geological evidence from lunar rocks brought back by Apollo missions shows the moon once possessed a magnetic field generated by its core, similar to Earth's protective magnetosphere. This ancient magnetic field, which existed billions of years ago, gradually faded as the core cooled and solidified. However, recent seismic data suggests the core might still be active in subtle but measurable ways. The core's structure includes a partial melt layer at the base of the lunar mantle, approximately 150 kilometers thick, which sits above the liquid outer core. This complex internal architecture indicates that the moon's interior remains more dynamic than the simple cooling model previously accepted by planetary scientists. Apollo's legacy and modern seismic discoveries. NASA's Apollo missions first placed seismometers on the moon between 1969 and 1977, with the Apollo 11 passive seismic experiment marking humanity's first attempt to listen to another world's internal activity. These instruments detected moonquakes and revealed some internal activity, recording about 100 to 200 meteorite impacts during their operational lifetime and detecting several categories of seismic events. However, the resolution of those 1970s instruments was limited by the technology available at the time. The Apollo seismometers operated until September 1977, providing valuable but incomplete data about lunar seismic activity. Now, with advanced sensors and modern analysis techniques, scientists are uncovering new categories of seismic events that were previously undetectable. These include deep moonquakes caused by tidal forces with Earth, shallow quakes with tectonic origins, and thermal quakes caused by extreme temperature fluctuations between lunar day and night. The new data suggests the moon's interior is more dynamic than once thought, with ongoing processes that continue to shape its internal structure even today. The shrinking moon theory and tectonic activity. One of the most intriguing hypotheses emerging from recent research is that the moon is slowly shrinking as its core continues to cool and solidify over geological time. This gradual contraction causes stress in the brittle lunar crust, leading to the formation of tectonic ridges, fault lines, and surface scarps that are surprisingly young in geological terms. Recent studies have identified hundreds of previously unknown ridges on the moon's surface, some of which may have formed as recently as 200 million years ago, a blink of an eye in geological terms. Using advanced mapping techniques and crater counting methods, scientists determined that these small ridges are younger than other features in their surroundings, meaning the moon's crust is still shifting and evolving today. This slow contraction and associated seismic activity could explain the mysterious seismic pulses detected recently, suggesting the moon is still adjusting internally as it continues its billion-year cooling process. The discovery challenges the long-standing belief that the moon became geologically dormant billions of years ago, and suggests that internal forces are still shaping its surface in measurable ways.
Earth-Moon gravitational dance and climate implications.
The implications of the moon's internal activity extend far beyond lunar science, potentially affecting Earth's long-term climate stability and orbital dynamics. The moon's gravitational influence stabilizes Earth's axial tilt at 23.5 degrees, which regulates our seasons and prevents chaotic climate swings that would make complex life difficult to sustain. Changes in the moon's mass distribution due to core activity and internal restructuring could subtly affect this crucial gravitational relationship over timescales of millions of years. While these effects are not immediate or catastrophic, they could influence Earth's climate cycles, tidal patterns, and even the Milankovitch cycles that govern ice ages over geological epochs. Michio Kaku has emphasized that the moon acts like a cosmic stabilizer, preventing Earth from wobbling chaotically like other planets of similar size. This stability has allowed for the slow, steady development of ecosystems and eventually human civilization. The moon's gravitational pull creates not just ocean tides, but also slight bulges in Earth's crust, generating heat through friction that contributes to our planet's internal warmth and geologic activity.
Next-generation lunar seismic monitoring.
NASA is preparing to deploy revolutionary new seismic instruments on the moon as part of upcoming Artemis missions, representing a quantum leap forward in our ability to monitor lunar internal activity. The Farside Seismic Suite, scheduled to land in Schrödinger Basin around 2026, will be the first seismic station placed on the moon's far side since the Apollo era. These next-generation seismometers will be approximately 30 times more sensitive than Apollo-era equipment, capable of detecting ground motions smaller than a single hydrogen atom. The Very Broadband Seismometer, originally designed for Mars InSight mission, represents the most sensitive seismometer ever built for space exploration. Additionally, the Lunar Environment Monitoring Station will establish a long-duration seismic station near the South Pole, where NASA's Artemis missions plan to build a permanent human presence. Unlike Apollo instruments that operated for limited periods, these new systems are designed to continuously monitor lunar seismic activity for months or even years, providing unprecedented insights into the moon's internal dynamics.
AI revolutionizes Apollo-era data analysis.
Artificial intelligence is playing, a crucial role in revolutionizing our understanding of lunar seismic activity by analyzing decades-old Apollo data with unprecedented precision. It's like machine learning algorithms are detecting patterns and anomalies in the original seismic recordings that human analysts missed or dismissed as noise during the 1970s analysis. These sophisticated AI systems can distinguish between genuine lunar activity and instrument artifacts with remarkable accuracy, flagging seismic events that didn't fit expected patterns and were often filtered out as measurement errors decades ago. NASA scientists describe this process as revolutionary, comparing it to having a conversation with someone for 50 years and suddenly realizing you've been missing half of what they've been saying. The AI analysis has revealed entire categories of seismic events occurring beneath the lunar surface that were completely missed by previous analysis techniques. These aren't just minor tremors but signatures of complex processes happening in the moon's core that provide new insights into its internal structure and ongoing geological activity. This technological breakthrough is helping scientists reconstruct a completely new picture of the moon's internal dynamics and the seismic pulse that has drawn Michio Kaku's attention.
Lunar exploration safety and future mission planning.
So, the discovery of ongoing seismic activity on the moon, well, it really raises some critical safety considerations for future lunar exploration and colonization efforts. Human missions and those mining operations planned near the lunar South Pole, they've got to carefully consider the risks posed by tectonic activity and potential moonquakes that could damage habitats or endanger astronauts. Understanding fault zones and stress patterns is just essential if we want to ensure the safety and stability of lunar habitats and infrastructure. Unlike Earth, the moon's crust doesn't have water circulation to heal cracks naturally, so once we fracture its brittle surface through mining or construction, those fractures could stick around and potentially trigger even larger seismic events. NASA's upcoming seismic networks will be absolutely vital for mapping these geological hazards and guiding mission planning for the Artemis program. The lunar regolith, which is that layer of loose material covering the moon's surface, actually sits atop a pretty complex network of faults and stress zones that could be disturbed by human activity. Future lunar bases are going to be completely dependent on their structural integrity, making seismic monitoring crucial for astronaut safety, and a habitat breach caused by unexpected seismic activity could be catastrophic, exposing crew members to the vacuum of space with very little warning or opportunity for evacuation.
A rare cosmic window for scientific discovery.
Michio Kaku emphasizes that humanity exists in a rare cosmic window, a fleeting moment in astronomical time when the moon's internal activity is still detectable before it eventually ceases forever. In another billion years or so, the moon's core may freeze solid completely, ending the geological processes we can observe today. This unique opportunity allows scientists to study planetary evolution processes that happen over billions of years, providing insights that, honestly, can't be obtained any other way. The moon is pretty much giving us a live demonstration of how small planetary bodies evolve and eventually become geologically inactive, serving as a sort of natural laboratory for understanding planetary death. Insights gained from studying the moon's core activity can inform our understanding of other rocky bodies in the solar system and beyond, including potentially habitable exoplanets. By watching the moon transition from a molten core to a solid one, scientists gain crucial insights into how different-sized worlds evolve, whether they can maintain protective magnetic fields, and their potential for supporting life. Kaku explains that we're incredibly fortunate to exist at exactly the right moment to witness the final chapters of the moon's geological story.
The moon as a key to planetary evolution.
The moon's seismic signals represent far more than just scientific curiosities. They're actually fundamental keys to understanding planetary life cycles throughout the universe. As the moon's core continues to cool and solidify, it offers researchers an unprecedented live demonstration of how small planetary bodies evolve and eventually die, providing crucial data for planetary science models. This knowledge is particularly vital as humanity prepares to return to the moon and establish a permanent presence there. Understanding the moon's internal processes helps scientists identify potentially habitable exoplanets and predict how their geological evolution might affect their ability to support life over billions of years. The moon serves as an intermediate step in planetary development, larger than asteroids but smaller than Earth-like planets, giving us really important insights into how different-sized worlds evolve. By studying how the moon's core solidifies and loses its magnetic field, scientists can develop models that predict how long smaller rocky exoplanets might maintain their protective magnetic shields. Michio Kaku's warning reminds us that the moon still holds secrets that could totally reshape our understanding of planetary science, Earth's future, and our place in the cosmic neighborhood. The moon is no longer the silent, dead rock we once thought it was. Thanks to new seismic discoveries and Michio Kaku's warnings, we now know it's a dynamic world with an active interior that could even influence Earth itself. As we prepare to return and explore further, understanding these internal processes is more important than ever before. Stay tuned for more updates on lunar science and the future of space exploration. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic insights. When astronomers discovered Oumuamua in 2017, they thought they'd found a typical interstellar visitor, just a chunk of rock from another star system passing through our cosmic neighborhood. But, 7 years later, the more we learn about interstellar objects, the stranger Oumuamua becomes. The recent discovery of 2 I/Borisov and now 3 I/Atlas has given scientists a baseline for what normal interstellar objects should look like. The problem? Oumuamua doesn't match the pattern at all. Today we're exploring how new interstellar discoveries are making our first cosmic visitor look increasingly alien and mysterious.
The discovery of 3I Atlas.
January 2025 marked a milestone in astronomy, when the Atlas asteroid survey detected what appeared to be a routine asteroid, designated C2023A3. However, months of orbital analysis revealed something extraordinary. This wasn't a solar system object at all, but our third confirmed visitor from interstellar space. Larry Deneau, principal investigator of the Atlas project at the University of Hawaii, initially dismissed the object as typical space debris until precise astrometry revealed its hyperbolic trajectory. Unlike Oumuamua's mysterious behavior, 3I/Atlas behaved exactly as astronomers expected an interstellar comet should. As it approached the sun, the object developed a classic comet tail, began outgassing water vapor and carbon monoxide, and showed predictable brightness variations consistent with a rotating, icy nucleus. Robert Warwick, the same astronomer who discovered Oumuamua with the Pan-STARRS telescope, confirmed that 3I/Atlas displayed all the characteristics absent from our first interstellar visitor. The object's composition matched theoretical predictions for comets formed in other star systems, with spectroscopic analysis revealing familiar water ice, carbon dioxide, and rocky material. This normal behavior made Oumuamua's anomalies even more puzzling and significant.
The Oumuamua discovery.
October 19, 2017, changed our understanding of the cosmos, when Pan-STARRS 1 telescope in Hawaii detected a fast-moving object unlike anything seen before. Robert Warwick was conducting routine asteroid observations when he noticed an object moving too quickly to be bound by the sun's gravity. Initially catalogued as C2017U1, then reclassified as A2017U1, when no comet tail appeared, the object finally received the designation 1I/Oumuamua, the first confirmed interstellar visitor to our solar system. The Hawaiian name means scout or messenger from afar, chosen by the Pan-STARRS team to honor its discovery location. Oumuamua was already leaving the solar system when detected, having made its closest approach to the sun weeks earlier. The object's discovery timeline was incredibly tight. Astronomers had only a few weeks to observe it before it faded beyond detection limits. European Southern Observatory's Very Large Telescope and other major observatories worldwide immediately began tracking campaigns. The International Astronomical Union had to create an entirely new designation system for interstellar objects, with the I prefix distinguishing visitors from other star systems from ordinary asteroids and comets born in our solar system.
Oumuamua's strange properties.
Oumuamua defied every expectation astronomers had about interstellar objects through its bizarre physical characteristics and behavior. The object measured approximately 400 meters long and only 40 meters wide, creating an unprecedented 10-to-1 aspect ratio that made it the most elongated object ever observed in space. Alan Fitzsimmons from Queen's University Belfast led spectroscopic studies revealing that Oumuamua's surface was dark reddish in color, similar to objects in the outer solar system that have been irradiated by cosmic rays for millions of years. The object rotated every 7.3 hours, creating dramatic brightness variations as different faces reflected varying amounts of sunlight toward Earth. Unlike typical asteroids or comets, Oumuamua showed no signs of outgassing, dust production, or tail formation, despite passing close to the sun, where volatile materials should have vaporized. Marco Michelli from the European Space Agency discovered that the object was gradually accelerating away from the sun, behavior that suggested comet-like outgassing but without any visible evidence of gas or dust emission. Temperature modeling indicated that Oumuamua's surface should have been hot enough to sublimate water ice, yet no outgassing was detected by even the most sensitive instruments available to astronomers worldwide.
The acceleration mystery.
The most perplexing aspect of Oumuamua emerged when, precise astrometric measurements revealed the object was accelerating away from the sun without any visible mechanism to explain this behavior. Marco Michelli and his team at the European Space Agency used Hubble Space Telescope observations combined with ground-based tracking data to determine that Oumuamua was experiencing a small but measurable non-gravitational acceleration. The acceleration was approximately 100,000th of a meter per second squared, tiny, but significant enough to affect the object's trajectory over time. For typical comets, this type of acceleration results from the rocket effect of outgassing materials as solar heating vaporizes ice and other volatiles from the nucleus. However, Oumuamua showed absolutely no signs of outgassing, dust production, or comet tail formation that would account for the observed acceleration. Davide Farnocchia from NASA's Jet Propulsion Laboratory confirmed that the acceleration was real and not an artifact of observational error or gravitational perturbations from known solar system bodies. The mystery deepened when astronomers realized that the acceleration was decreasing as Oumuamua moved farther from the Sun, exactly matching the pattern expected from solar-powered outgassing, but without any detectable outgassing occurring.
Scientific investigations.
NASA's Spitzer Space Telescope conducted crucial observations that, honestly, deepened the Oumuamua mystery rather than solving it. Davide Farnochia led the Spitzer investigation, searching for any infrared signature that might indicate outgassing or thermal emission from the object's surface. The results were shocking. Spitzer detected no thermal emission whatsoever, suggesting Oumuamua's surface was either extremely small or highly reflective. The albedo measurements indicated that Oumuamua reflected approximately 10 times more sunlight than typical asteroids, giving it an unusually bright mirror-like surface. Alan Harris from the German Aerospace Center collaborated on thermal modeling that revealed Oumuamua must be either much smaller than initially estimated or composed of highly reflective material, unlike any known solar system object. The James Webb Space Telescope was unfortunately not yet operational during Oumuamua's passage, but ground-based spectroscopy by teams led by Alan Fitzsimmons revealed a surface composition that appeared similar to organic-rich asteroids from the outer solar system. However, the complete absence of water vapor, carbon monoxide, or dust emission remained unexplained by any conventional model of interstellar object composition and behavior.
The alien hypothesis.
Abraham Loeb, chair of Harvard University's astronomy department, sparked worldwide controversy by proposing that Oumuamua might be an artificial object created by extraterrestrial intelligence. In his analysis published in astrophysical journal Letters with Shmuel Bialy, Loeb suggested that Oumuamua's unusual acceleration could be explained if it were a light sail, an ultra-thin sheet of material propelled by solar radiation pressure. The hypothesis proposed that Oumuamua might be debris from alien technology, possibly a defunct probe or even a deliberately sent investigation device from another civilization. Loeb calculated that a sail-like object only millimeters thick but hundreds of meters wide could experience exactly the type of acceleration observed without requiring outgassing. The artificial origin theory gained traction when Loeb noted that Oumuamua's extreme elongation and high reflectivity were consistent with constructed materials rather than natural rock or ice. NASA's reaction was skeptical but respectful, with Thomas Zurbuchen, former associate administrator for science missions, acknowledging that extraordinary claims required extraordinary evidence but shouldn't be dismissed without investigation. Loeb's hypothesis divided the scientific community, with many astronomers arguing that natural explanations should be exhausted before considering extraterrestrial origins for unusual but not impossible celestial phenomena.
The dark comet theory.
Darrell Seligman from the University of Chicago and Gregory Laughlin from Yale University proposed a natural explanation for Oumuamua's mysterious behavior through their innovative dark comet hypothesis. Their theory suggested that Oumuamua was composed primarily of hydrogen ice, frozen molecular hydrogen that would be invisible to most telescopes and leave no detectable outgassing signature. Hydrogen ice sublimates at extremely low temperatures and produces gas that's nearly impossible to detect with conventional instruments, potentially explaining the acceleration without visible outgassing. The theory required Oumuamua to have formed in an exceptionally cold environment, possibly in the outer regions of another star system where temperatures were low enough for hydrogen to freeze solid. Seligman calculated that objects composed of hydrogen ice could maintain their integrity during interstellar travel, and would begin sublimating as they approached any star, producing the rocket-like acceleration observed. The hydrogen ice hypothesis gained support from theoretical models, showing that such objects could form naturally in protoplanetary disks under specific conditions. However, the theory faced criticism because hydrogen ice has never been observed in space, and would require extraordinary preservation during Oumuamua's millions of years journey through interstellar space before reaching our solar system.
The ongoing debate.
Abraham Loeb remained unconvinced by the dark comet theory, publishing detailed critiques arguing that the hydrogen ice hypothesis created more problems than it solved. In his book Extraterrestrial, the First Sign of Intelligent Life Beyond Earth, Loeb pointed out that hydrogen ice would require formation temperatures of -434 degrees Fahrenheit, colder than most regions of interstellar space. He argued that such an object would likely sublimate completely during its journey to our solar system. making survival impossible over the millions of years required for interstellar travel. Daryl Seligman responded with refined calculations showing that sufficiently large hydrogen ice objects could retain enough material to remain intact, but acknowledged the theory required exceptional formation conditions. The scientific community remained divided, with most astronomers favoring natural explanations while acknowledging the limitations of current observational data. European Southern Observatory astronomers conducted follow-up studies of other interstellar objects, finding that normal comets like 2I/Borisov behaved exactly as traditional comet models predicted, making Oumuamua's anomalies even more striking. The debate highlighted fundamental gaps in our understanding of interstellar object formation and composition that persist today.
Project Lyra mission concept.
Andreas Hein from the Initiative for Interstellar Studies and Zach Manchester from Stanford University developed Project Lyra, an ambitious mission concept designed to intercept and study Oumuamua before it disappears forever into interstellar space. The proposed mission would require launching by 2025 to have any chance of reaching the object, using Jupiter and possibly Saturn for gravitational assists to achieve the enormous velocity needed. ESA's Advanced Studies program examined the technical feasibility, concluding that a small CubeSat could theoretically reach Oumuamua by 2054 if launched on a powerful rocket like NASA's SLS or SpaceX's Falcon Heavy. The mission would carry miniaturized instruments including cameras, spectrometers, and possibly a penetrator to sample the object's interior composition. Project Lyra faces enormous technical challenges, including the need for spacecraft to survive decades in space while maintaining operational capability upon arrival. The mission cost estimates range from $500 million to several $billion, making it financially challenging for most space agencies. Despite these obstacles, Project Lyra represents humanity's best chance to definitively determine Oumuamua's true nature and resolve the debate between natural and artificial origins that has captivated both scientists and the public worldwide.
The future hunt.
The Vera C. Rubin Observatory, beginning operations in 2025, promises to revolutionize our ability to detect and study interstellar visitors before they leave the solar system. Mario Jurek from the University of Washington leads the Legacy Survey of Space and Time that will discover an estimated 1 interstellar object per year, a dramatic increase from our current rate of discovery. The observatory's wide-field camera and rapid survey capabilities will provide weeks or months of advance warning when interstellar objects approach, allowing detailed study missions to be planned and executed. NASA's Interstellar Probe mission, currently in development, could potentially encounter interstellar objects during its journey beyond the solar system. The comparison between Oumuamua 2I/Borisov and 3I/Atlas has already revealed that our first visitor was genuinely anomalous, rather than representative of typical interstellar objects. As we discover more interstellar visitors, the statistical sample will help determine whether Oumuamua was a rare natural phenomenon or something more extraordinary. The scientific consensus suggests that while artificial origins remain possible, natural explanations involving exotic compositions or formation mechanisms are more likely. However, the mystery of Oumuamua has permanently changed how astronomers approach the study of interstellar objects and the search for potential technosignatures in space. Oumuamua arrived as a mysterious messenger from another star system and left as one of astronomy's greatest unsolved puzzles. The discovery of normal interstellar objects like 2I/Borisov and 3I/Atlas has only made our first visitor appear more anomalous and extraordinary. Whether it was exotic hydrogen ice, alien technology, or something we haven't yet imagined, Oumuamua proved that the universe still holds surprises that challenge our understanding. Subscribe to Stellar Tech for more cosmic mysteries that push the boundaries of science and keep us wondering what else might be traveling between the stars. It's difficult for us humans to fully comprehend the enormity of space. We're comfortable in our own cosmic neighborhood, the solar system, and are used to familiar faces like Jupiter, Mars, and of course Earth. But beyond the heliopause lies the cold oblivion of interstellar space. Only 3 confirmed objects have ever crossed this threshold into our domain. These were the famous Oumuamua in 2017, Borisov in 2019, and now 3I/Atlas in 2025, visitors that bring with them both scientific excitement and perhaps even a hint of cosmic fear about what else might be traveling between the stars.
Beyond the heliopause, our interstellar visitors.
The vast expanse beyond our solar system represents one of the most hostile environments imaginable, a realm where temperatures approach absolute zero, and the nearest stars are separated by trillions of miles of empty void. Yet occasionally, objects from these distant stellar nurseries complete journeys lasting millions of years to visit our cosmic neighborhood. Interstellar space begins beyond the heliopause, approximately 120 astronomical units from the Sun, where our star's solar wind can no longer push back against the interstellar medium. Dr. Alan Stern from the Southwest Research Institute describes this boundary as humanity's cosmic doorstep, beyond which lies the true wilderness of the galaxy. The detection of interstellar visitors requires objects to exhibit hyperbolic orbits, trajectories that prove they're not gravitationally bound to our Sun and must have originated elsewhere. NASA's definition requires orbital eccentricity greater than 1.0 and excess velocity that cannot be explained by gravitational acceleration from solar system bodies. These mathematical signatures distinguish true interstellar objects from long-period comets that merely appear to come from great distances. The rarity of such detections makes each visitor precious, windows into the composition and formation processes of distant planetary systems that we may never reach with conventional spacecraft. The third visitor, 3I/Atlas discovery. January 2, 2025 marked a historic day in astronomy when the Atlas Asteroid Survey detected an unusual object that would soon become our third confirmed interstellar visitor. Dr. Larry Deneau from the University of Hawaii was monitoring the automated detection systems when object A11PL3Z appeared in the survey data, moving at an extraordinary velocity that immediately flagged it as anomalous. Unlike typical asteroids that follow predictable elliptical orbits, this object displayed hyperbolic motion characteristic of visitors from interstellar space. Dr. Robert Warwick, the astronomer who discovered both Oumuamua and helped confirm Borisov, led the initial follow-up observations that confirmed the object's interstellar origin. The Minor Planet Center in Cambridge, Massachusetts coordinated rapid confirmation observations from telescopes worldwide, including the Canada-France-Hawaii Telescope and Gemini Observatory. Within 72 hours, enough orbital data had been collected to definitively prove that A11PL3Z was traveling too fast to be gravitationally bound to our solar system. The object's discovery represents a milestone in astronomical detection capabilities, the first interstellar visitor found by automated survey systems rather than manual observation. 3I/Atlas received its final designation after the International Astronomical Union confirmed its interstellar trajectory and cometary activity, making it officially the third known visitor from beyond our solar system. The Atlas Survey System. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, represents a revolutionary approach to sky surveillance, designed primarily to detect potentially hazardous asteroids, but proving equally capable of finding interstellar visitors. Dr. John Tonry from the University of Hawaii leads the project, which operates 4 telescopes across Hawaii and South Africa, continuously scanning the entire visible sky every 24 hours. Each ATLAS telescope uses a 0.5-meter mirror equipped with advanced CCD cameras, capable of detecting objects as faint as magnitude 19.5. The system processes approximately 100 terabytes of data monthly, using sophisticated algorithms to identify moving objects against the background of stars. ATLAS distinguishes itself through rapid cadence observations, taking multiple images of the same sky regions within hours to detect object motion. The discovery of 3I/Atlas validated the system's ability to detect rare phenomena beyond its primary mission. Dr. Deneau noted that the automated nature of ATLAS allows us to catch objects that human observers might miss due to their subtle motion or unusual characteristics. The system's success has prompted NASA to fund expansion to additional sites, creating a global network capable of providing even earlier warnings for both hazardous asteroids and interstellar visitors that might otherwise escape detection. From A11PL3Z to C2025N1, the naming journey. The designation journey of 3I/Atlas really illustrates the complex process astronomers use to classify and name celestial objects. So, initially it was designated A11PL3Z by the Atlas Survey System, but, as its true nature became apparent, the object underwent multiple reclassifications. Dr. Gareth Williams at the Minor Planet Center explained that automated survey systems use temporary alphanumeric codes before official designations are assigned. Once hyperbolic orbital motion was confirmed, the object received the provisional designation C/2025N1, which indicates a comet discovered in the first half of July 2025. The C/prefix denotes a non-periodic comet, while 2025N1 tells us it was the first comet found during the 14th half-month period of that year. As observations revealed clear cometary activity, including coma formation and tail development, the International Astronomical Union assigned the final designation 3I/Atlas. The 3I prefix marks it as the third interstellar object, following 1I/Oumuamua and 2I/Borisov. The Atlas portion honors the survey system that discovered it, following IAU traditions of crediting discoverers. This naming evolution really reflects the careful verification process required to confirm interstellar origin, ensuring that only objects with definitively hyperbolic orbits receive the prestigious EIN designation reserved for visitors from other star systems. A hyperbolic journey at 58 kilometers per second. 3I/Atlas approaches our solar system with a hyperbolic excess velocity of 58 kilometers per second, a speed that definitively proves its interstellar origin and provides clues about its cosmic journey. Dr. Davide Farnochia from NASA's Jet Propulsion Laboratory calculated that this velocity places 3I/Atlas among the fastest interstellar visitors ever detected, suggesting either a recent gravitational encounter with another star or acceleration from its parent system. The object's trajectory indicates it entered our solar system from the direction of the constellation Lynx, possibly originating from the Vega stellar system, which is about 25 light-years away. Orbital mechanics reveal that 3I/Atlas has been traveling through interstellar space for an estimated 1 to 3 million years before encountering our solar system's gravitational influence. The object's perihelion, its closest approach to the Sun, occurred on October 30, 2025, at a distance of 0.65 astronomical units, which is well within Earth's orbital radius. Dr. Alan Harris from the German Aerospace Center noted that this close solar approach provides optimal conditions for studying the object's composition through spectroscopic analysis and thermal emission observations. The hyperbolic nature of the orbit means 3I/Atlas will never return. After its solar encounter, the object will be gravitationally accelerated by our Sun, eventually reaching speeds exceeding 70 kilometers per second as it exits toward the constellation Draco. Brightness, rotation, and the 29-hour cycle. Photometric observations of 3I/Atlas have revealed a complex 29-hour rotation period that provides crucial insights into the object's shape, composition, and structural integrity. Dr. Alan Fitzsimmons from Queen's University Belfast leads the International Photometry Campaign, coordinating observations from telescopes worldwide to track the object's brightness variations over time. The 29-hour cycle shows magnitude variations of approximately 1.5, which indicates either a highly elongated shape similar to Oumuamua or surface features with dramatically different reflectivity properties. Light curve analysis by Dr. Mikael Granvik from the University of Helsinki suggests the object is likely tumbling rather than rotating around a single axis, which is consistent with an object that has experienced gravitational perturbations or impacts during its interstellar journey. The rotation period is significantly longer than typical solar system comets, which usually rotate every 6 to 12 hours due to outgassing torques. Thermal infrared observations using the Spitzer Space Telescope show that 3I/Atlas maintains surface temperatures consistent with its distance from the Sun, but with unusual temperature distribution patterns that suggest non-uniform surface composition. The object's brightness peaked at approximately magnitude 10 during perihelion, making it visible to experienced amateur astronomers using moderate-sized telescopes, but remaining too faint for naked-eye observation, despite its considerable size. Coma, tail, and cometary activity. Unlike the mysterious Oumuamua, 3I/Atlas displays clear cometary activity which has, provided astronomers with valuable data about its composition and structure. Dr. Matthew Knight from the University of Maryland leads studies of the object's coma, the fuzzy atmosphere of gas and dust surrounding the nucleus as solar heating vaporizes surface materials. The coma began developing when 3Y Atlas reached approximately 2.5 astronomical units from the Sun, initially appearing as a faint envelope around the central nucleus. Spectroscopic analysis by Dr. Michael DeSanti from NASA Goddard Space Flight Center detected emissions from water vapor, carbon monoxide, and hydrogen cyanide, typical signatures of comet sublimation, but with unusual abundance ratios. The object developed a visible tail reaching lengths of 200,000 kilometers as it approached perihelion, composed primarily of dust particles ejected by outgassing. High-resolution imaging from the Hubble Space Telescope revealed the tail's structure shows periodic variations corresponding to the object's rotation, indicating active regions on the nucleus surface. Dr. Jacqueline Keene from Boston University noted that the gas production rate of 3Y Atlas is approximately 10 times higher than expected for its estimated size, suggesting either unusual composition or internal structure. The cometary activity confirms 3Y Atlas as a volatile-rich object that formed in the outer regions of another stellar system, where temperatures were low enough for water and other compounds to condense.
Oumuamua versus Borisov versus 3I/Atlas.
So let's compare these three confirmed interstellar visitors: Oumuamua, Borisov, and 3I/Atlas. They really present a fascinating study in contrasts, revealing just how diverse the objects traveling between stellar systems can be. Oumuamua, which was discovered by Dr. Robert Warwick back in 2017, is still the most enigmatic of the bunch. It showed no cometary activity, even when it got close to the Sun, and it had this unexplained acceleration and extreme elongation that made it, well, truly unique among known solar system objects. On the other hand, 2I Borisov, which was found by amateur astronomer Gennady Borisov in 2019, behaved exactly as astronomers expected an interstellar comet would. It developed a classic tail, showed predictable outgassing, and had a composition pretty similar to solar system comets. Then there's 3I Atlas, which represents something kind of in-between. It displayed clear cometary activity but with some unusual characteristics that set it apart from typical comets. Dr. Stefano Bagnulo from Queen's University Belfast led comparative studies showing that Borisov had carbon monoxide ratios similar to solar system comets, while 3Y Atlas showed significantly different volatile abundances. When it comes to size, estimates put Oumuamua at around 400 meters long, Borisov at roughly 1 kilometer in diameter, and 3Y Atlas at an estimated 5 to 10 kilometers across, making it potentially the largest interstellar visitor we've detected so far. All this suggests that Oumuamua might represent a rare class of objects, while Borisov and 3I Atlas indicate that typical interstellar comets actually share a lot of characteristics with their solar system cousins.
A 3 billion 11-year-old traveler.
Determining the age of 3I Atlas is, honestly, one of the most challenging aspects of studying interstellar objects. It requires some pretty sophisticated modeling of cosmic weathering processes and orbital dynamics. Dr. Grigory Fedorets from Queen's University Belfast estimated the object's age to be somewhere between 3 and 11 billion years, based on its surface spectroscopic properties, and assumed travel times from nearby stellar systems. That's pretty wild. It means 3I Atlas could be older than Earth itself, having formed during those early epochs of galactic evolution, when star formation rates were way higher than they are today. Now, cosmic ray exposure modeling by Dr. Renu Malhotra from the University of Arizona suggests the surface should show significant radiation damage after billions of years in interstellar space, but interestingly, observations indicate a surprisingly pristine composition. The age estimates assume 3I Atlas originated from stellar systems within 100 light-years of our current galactic position, though honestly the actual birthplace could be much farther away, given the complex orbital motions of stars over galactic timescales. Dr. Fatih Namouni from Côte d'Azur Observatory calculated that objects of this age could have originated from star-forming regions that no longer even exist, having been dispersed by galactic rotation and stellar evolution. The ancient nature of 3I Atlas gives us, well, a unique opportunity to study materials from the early solar system formation epoch, potentially preserving chemical signatures from primordial stellar nebulae that formed billions of years ago.
October 30th, perihelion and beyond.
October 30th, 2025 marked the closest approach of 3Y Atlas to our Sun, giving astronomers around the world optimal conditions for detailed study of this ancient interstellar visitor. Perihelion observations coordinated by Dr. Casey Lise from Johns Hopkins Applied Physics Laboratory used, honestly, just about every major ground-based observatory and space telescope to capture as much scientific data as possible. The 0.65 AU closest approach placed 3Y Atlas well within Earth's orbit, allowing for unprecedented resolution observations of an interstellar object's nucleus and its active regions. Solar heating during perihelion triggered peak cometary activity with gas production rates reaching 10 to the 28th molecules per second and a tail stretching over 500,000 kilometers. Dr. Tony Farnham from the University of Maryland reported that high-resolution imaging revealed surface features and active jets similar to solar system comets, but, interestingly, with some unusual spatial distribution patterns. After perihelion, tracking shows that 3I Atlas will stay observable until about mid-2026 before fading beyond the detection limits of our current telescopes. The object's exit trajectory toward the Draco constellation has been calculated with precision, with a final velocity exceeding 75 kilometers per second as it leaves our solar system for good. Looking forward, future observations will focus on long-term monitoring of the tail's evolution and spectroscopic analysis of outgassing products, which will keep revealing secrets about interstellar comet formation and the chemical evolution of distant planetary systems. 3. I-Atlas has given astronomers an unprecedented opportunity to study pristine material from another star system, bridging billions of years and countless light-years to reach, well, our cosmic doorstep. This ancient traveler carries chemical signatures from stellar environments we may never visit, and its cometary activity proves that familiar processes are at work throughout the galaxy. As 3I Atlas continues its eternal journey beyond our solar system, it leaves behind invaluable data that expands our understanding of planetary formation all across the cosmos. Be sure to subscribe to Stellar Tech for more discoveries about our universe's most distant messengers. For decades, we've looked at the moon as the final milestone of a bygone era, a silent gray world covered in dust and craters. But the age of lunar stagnation is over. China's ambitious space program has sent back not just rocks, but a technological revelation, a discovery that reboots our entire understanding of the moon's potential and sparks a new technological race to our celestial doorstep. This isn't just about exploration, it's about the technology that will define our future off-world. Let's power up and explore the details. Anomalous lunar structures. The modern debate about strange objects on the moon was largely ignited by the declassified data from the 1994 Clementine mission. This was a unique partnership between NASA and the United States Department of Defense, designed to space test advanced sensor and imaging technology by putting it through its paces mapping the moon. While it achieved its technical objectives, the 1.8 million images it returned have been scrutinized for decades for more than just their scientific value. On the moon's far side, a region permanently shielded from our view, some of these images contain features that appear to challenge natural formation theories. Analysts point to formations with strikingly geometric properties and what seem to be the remnants of large broken-down structures. The most cited example is a feature that has been dubbed the pyramid due to its seemingly flat sides and sharp angular peak. The official scientific explanation is that these are simply visual illusions created by a combination of low sun angles, complex geology, and digital compression artifacts from early imaging technology. However, critics argue that specific sections of these images exhibit unusual blurring, suggesting a deliberate attempt to obscure sensitive data, and that the mission's true purpose was a technological reconnaissance of something unexpected. Ancient astronaut connections. The speculation around lunar anomalies is a key pillar of the ancient astronaut hypothesis, which reframes ancient history as a record of human interaction with advanced extraterrestrial technology. This theory examines old myths and artifacts, searching for descriptions of what might be advanced engineering. A famous, though thoroughly debunked piece of lore is the alleged secret audio from Apollo 11, where Neil Armstrong supposedly describes seeing alien spacecraft. While untrue, it fuels the narrative. This perspective reinterprets ancient texts, like the Sumerian tablets' description of the Anunnaki gods. When a deity instructs his son to wear an eagle's mask for a lunar journey, theorists don't see mythology, they see a technical manual describing a breathing helmet. This technological reinterpretation is applied to artifacts worldwide, including the Wandjina cave paintings in Australia. The figures depicted with their large dark eyes and halo-like helmets are seen not as spirits but as visitors in advanced environmental suits. The theory asks a compelling question: if an early human saw an astronaut today, would they draw a god or a person in a machine? China's groundbreaking discovery. While theories of ancient tech remain debated, China's space program has delivered undeniable technological triumphs. The Chang'e 5 mission in December 2020 was an engineering marvel of automation and robotics. It executed a precision landing, deployed a sophisticated drilling and scooping mechanism to collect nearly 2 kilograms of lunar material from different depths, and then successfully launched an ascent vehicle from the moon's surface, a feat of remote rocketry. After the precious cargo was returned to Earth, Chinese material scientists made 2 incredible announcements. First, they identified a previously unknown crystal in the samples, naming it Change Site Y. This made China only the 3rd country to discover a new mineral on the moon, showcasing their advanced analytical capabilities. Second, and more importantly, their instruments detected water molecules. This water wasn't in the form of ice but was physically trapped inside microscopic beads of glass that were forged billions of years ago in the intense heat of meteorite impacts. This discovery was a technological game-changer, proving that a vital resource for any off-world operation is far more abundant and accessible than previously thought. Revolutionary implications. The confirmation of widespread water on the moon is honestly the single most important technological enabler for humanity's future in space. It makes the engineering principle known as in situ resource utilization, or ISRU, a viable strategy. For decades, the sheer cost of launching every drop of water and ounce of fuel from Earth's deep gravity made the idea of a permanent lunar base, prohibitively expensive. China's discovery changes that financial and logistical calculus entirely. The lunar soil, or regolith, may hold billions of tons of this trapped water. The technology to extract it is actually pretty straightforward. Robotic rovers could be designed to heat the regolith, releasing the water as vapor to be collected. Now this water can sustain life, but its true value is in what it can be converted into. Using electrolysis powered by solar panels, the water molecules can be split into pure hydrogen and oxygen. These are the 2 most potent and efficient components of modern chemical rocket fuel. This technology would allow the moon to become a fully self-sufficient industrial outpost and a refueling depot, radically lowering the cost and increasing the payload capacity for missions to Mars and beyond. The Chang'e program evolution. China's success is honestly a case study in methodical, iterative technological development. Their lunar exploration program was designed as a series of increasingly sophisticated engineering challenges, with each mission serving as a testbed for the next. The program began with the Chang'e 1 and Chang'e 2 orbiters, which were essentially advanced robotic surveyors, creating the high-resolution maps needed for all future surface missions. The next phase was proving their landing technology. Chang'e 3 successfully put a lander and the U-2 rover on the surface in 2013. Having mastered landing, they tackled an even greater challenge with Chang'e 4 in 2019, a landing on the far side of the moon. This required an entirely new piece of infrastructure, a dedicated communications relay satellite positioned in a stable orbit beyond the moon to bounce signals back to Earth. With landing and long-range communication perfected, they moved to the final, most complex phase sample return. The Chang'e 5 mission integrated all of these technologies and added several new ones, including a robotic ascent vehicle and an automated orbital rendezvous system. This deliberate, step-by-step evolution of their tech stack is what has propelled China to the forefront of lunar exploration. Resource revolution on the moon. The Chang'e 5 samples have honestly ignited a technological and economic revolution by confirming the moon's status as a treasure trove of 21st century resources. The new mineral, Change Site Y, is a carrier of an isotope called helium-3. Deposited by solar winds over billions of years, helium-3 is incredibly rare on Earth but abundant on the moon. It is the most sought-after fuel for next-generation nuclear fusion reactors. The technology of helium-3 fusion promises to generate vast amounts of clean, safe energy without the long-term radioactive waste of current fission reactors. The technology to mine and process lunar helium-3 could literally power the Earth for centuries. Furthermore, the lunar regolith is a rich source of rare Earth elements, which are the backbone of our modern high-tech world, used in everything from powerful magnets and electric motors to the electronics in our phones and computers. Developing the advanced robotics and automated mining technologies required to extract these resources on the moon would not only fuel a new space economy, but would also provide a secure and environmentally superior alternative to terrestrial mining operations. Future lunar colonization. With the key technological barriers of water, energy, and materials now seemingly solved, the engineering challenge of building a permanent human base on the moon has come into sharp focus. In March 2021, this moved from concept to formal policy, when China and Russia announced a joint initiative to construct the International Lunar Research Station, or ILRS. This project is a plan for a permanent, expandable, and eventually autonomous human outpost at the lunar South Pole. This site is considered prime real estate because its deep craters, permanently shielded from sunlight, are thought to hold vast reserves of water ice. The ILRS will be a test bed for a new generation of technologies, including closed-loop life support systems, advanced radiation shielding, and construction techniques like 3D printing habitats using native lunar regolith. To power this ambitious undertaking, China has announced plans to develop and deploy a powerful nuclear fission reactor on the moon by 2028. A foundational piece of technology that would provide the consistent energy needed for large-scale industrial operations and colonization efforts. Lunar resources, the new gold rush. The scientific confirmation of the moon's resource wealth has kicked off a high-tech gold rush, creating a global race to develop the technologies for lunar mining and resource extraction. The focal point of this competition is the moon's South Pole, now viewed as the key to a sustainable off-world presence. This technological race, however, is running ahead of international law. The 1967 Outer Space Treaty is the bedrock of space governance and clearly forbids any nation from claiming sovereignty over the moon. But it was written half a century before the technology for lunar mining was considered viable, and so it is dangerously silent on the legality of extracting and owning celestial resources. This legal ambiguity has created a Wild West environment where the First Nations or private companies that successfully demonstrate the technology to mine the moon could establish a powerful precedent, effectively shaping the economic and legal rules for everyone else. This is driving a frantic pace of innovation in robotics, remote sensing, and automated processing, as the finish line isn't just a scientific discovery, but the establishment of a technological foothold. International space race. The 21st century space race is defined by competing technological philosophies. The United States is pursuing its return to the moon through NASA's Artemis program, which is structured as a massive public-private partnership. This model outsources the development of critical hardware to innovative commercial companies. For example, NASA has tasked SpaceX with developing its reusable Starship Super Heavy rocket as the primary human landing system, and Blue Origin is building a competing lander. This strategy is designed to accelerate innovation and drive down costs by harnessing the competitive power of the commercial market. This approach is diplomatically extended through the Artemis Accords, an international framework that promotes shared principles for peaceful and transparent space exploration among its many signatory nations. This model of commercially driven, alliance-based development stands in stark contrast to the state-funded, vertically integrated approach of its primary competitors, setting the stage for a fascinating race between two different models of technological progress. Competition between China, US, and other nations. The new lunar race is solidifying into distinct technological blocks. On one side is the US-led Artemis Accords, a large coalition of nations pooling resources and adhering to a common set of operational standards. On the other is the strategic partnership between China and Russia, focused on the development of their joint lunar base, the ILRS, which is building its own coalition of international partners. But this is not merely a two-sided competition. Other nations are rapidly developing their own advanced space technologies and becoming major independent players. In 2023, India's space agency, ISRO, executed a flawless robotic landing with its Chandrayaan-3 mission, becoming the first country in history to successfully touch down near the lunar South Pole. This achievement demonstrated a mastery of advanced autonomous landing systems and put India at the forefront of the search for lunar water. This multipolar landscape, filled with competing government programs and disruptive private companies, is creating an ecosystem of rapid technological advancement. The immense engineering challenges ahead mean that while competition is the current driver, collaboration may be the ultimate key to success. The moon is no longer a distant monument to past glories. It is an active lab, a resource-rich frontier, and the essential technological proving ground for our multiplanetary future. China's discoveries have served as a catalyst, accelerating a new global race to develop the technologies that will allow us to live and work on another world. What piece of technology do you think is most critical for building a lunar base? Let us know your thoughts in the comments. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the stellar tech that is shaping our future. Thanks for watching Stellar Tech.